Días a todos, muchas gracias por estar aquí compartiendo una conferencia de la parte de la doctora Khodri. Yo soy el doctor Alessandro Liso, representante de IRD, por sus siglas en francés, un Instituto de Investigación para el Desarrollo, aquí en México, para México, América Central y Cuba, y también representante de Sorbonne Universidades aquí en la UNAM. Para mí es un placer presentarles, por supuesto, a la doctora Khodri. La doctora Khodri es investigadora del IRD en el laboratorio del océano en París, laboratorio que trabaja los procesos físicos del océano y su influencia en la variabilidad del clima en varias escalas del tiempo, incluyendo, por supuesto, el clima del pasado. La doctora Khodri es coordinadora en el laboratorio del océano de un grupo de investigación enfocado en los procesos de la variabilidad del clima tropical y los impactos sobre las regiones más vulnerables. La doctora Khodri es una experta en la variabilidad del clima y del océano durante los últimos 2000 años a través de modelos climáticos. Sus temas principales de investigación son actualmente la modelización del clima, los mecanismos de la variabilidad climática en los últimos siglos, el impacto de los forzantes solares y volcánicos sobre el clima y el sistema del monzón en Sudamérica. Dejo ahorita la palabra a la doctora Khodri. La doctora Khodri dictará su conferencia en inglés. Muchas gracias.
You hear me? Well, it's working? Yes. Thank you for the long and nice introduction. I don't think I needed that much detail, but thanks a lot, and thanks for having me today. So I'm going to try to be clear and talk about climate change and how we can learn from recent and future climate change from past climate observations relating both natural archives and direct instrumental observation to better understand the climate processes and evaluate our role as a native role in the climate mechanism. So that's why I'm here, because I think climate is an exciting science. I know that you're not all familiar with this, so I'll try to be very general. I think we are here in the Department of Geophysics and Geology, if I am correct. So maybe I hope you will be able to learn a few things about the climate research, and also to exchange with you and give you some scientific elements to understand why we are very much concerned about climate change, especially in the public and in the media. I think you all heard about the COP21 that just happened in France, Paris, end of last year. And so also to give you elements that can help you act as citizens to limit the impact of climate change. So just for a start, some take-home points that I'm going to try to develop during the presentation, and hopefully at the end you will have a better understanding and will be convinced that climate change is real, that we, people, are causing it, and that there is a widespread agreement among scientists that we are responsible for most of the climate change that occurred over the last decades, and that this climate change has mostly a negative impact on society, more than positive impact, but we can limit it. It's not that difficult if we choose to. So let's first start with the basics. What's climate? I wanted to make a short comment on this because people tend to be confused between climate and weather. Climate is not weather. Climate is defined by the long-term mean of various weather situations that occurs on a daily basis or a monthly basis, for example. And you need to average all these situations over a long time, usually it's about 20 or 30 years, to have like a good vision of the mean climate of a certain region. For example, the climate over France, Paris, has nothing to do with the climate here in Mexico, because it's not the same latitude and under same influence in terms of ocean circulation. So basically, the weather tells you what to wear, while the climate tells you what to buy, which kind of clothes you should buy. So I hope that's clear. So what are the mechanism of climate? What is a climate? In fact, climate is a heat engine, and it gets its energy mostly from solar radiation. That's basically the source of the climate engine. The solar radiation heat the ocean, the atmosphere, the land surface, and as any body, that has a certain temperature, like a human body or a chair or whatever, when it has a certain temperature, it would tend to reflect back or emit energy through infrared. So I guess you also images of cameras through infrared filters. We all have like emission of infrared radiation, and the Earth do the same. So basically, the mean balance between what the Earth gets as energy from the solar radiation minus what it's emitting through infrared radiation, so cooling the Earth by emitting infrared radiation towards the space. That's, if you make the difference between both, you get the heat balance that is available for the climate system. And since the Earth is a sphere, we would get more solar energy here over the tropical latitude than the pole, because there the radiation are like really like not intersecting a surface. And so you lose more heat through infrared radiation than you gain from solar radiation, as opposed to the tropical latitude where you will gain more solar radiation as compared to what you will lose through infrared radiation. So we have an excess of heat in the tropics as compared to a deficit of heat over the pole. And this is very important to know because that's the key to understand climate mechanism, at least the basis. So here, just to illustrate what I just said, here this is a satellite image of solar radiation that was received by the Earth in March 2001. So this is in watt per square meter. We received more solar radiation over the tropics, and of course less over the pole. This is in spring, so this is in the middle of the season. If I had shown the same picture in winter, we will have mostly nothing reaching polar region. That's why we have polar nights. And the Earth will reflect part of its energy because the various surfaces have some sort of reflectance power that we call albedo. For example, polar region, there is a lot of ice and snow, and they are very reflective towards solar radiation. That's why snow is white, because it reflects most of the solar spectrum that is received from the sun. The ocean also has a certain reflectance, and this measure goes from 1 to 7, for example. So we will reflect back a lot of energy here as compared to a polar region. And if you look at the radiation emission through infrared that I just mentioned before, you will see that the tropics that are more warm as compared to the polar region will lose more radiation through infrared emission as compared to polar region. So now if you net the net, if you compute the net balance, meaning the solar radiation that we receive minus what it's emitted, reflected back to space through the reflectance of the Earth's surface, minus what it's emitted through infrared radiation, the net heat gain for the Earth's surface will look like this in annual mean. So we have excess of energy in the tropics as compared to the pole. And this excess of energy is not going to stay here. The ocean and atmospheric fluids will want to redistribute this unbalance of energy through ocean and atmosphere circulation. So basically, the excess of heat that we will have over tropical latitude will be transported by ocean and atmospheric circulation toward where there is a deficit, meaning over a mean latitude. And this transport can be made in various ways, through meridional circulation in the ocean, but also in the atmosphere, and also through cyclonic circulation over mid-latitude. So basically, what I wanted to show through with this picture is that the heat engine of the climate system is really due to the fact that we receive more solar radiation in the tropics as compared to the pole. So now we know what's controlling the mean climate, that we have a warmer climate over low latitude as compared to higher latitude, that the ocean and the atmosphere are moving around to redistribute this energy. Now we all know that the climate is not stable, it varies, and it varies at any time scale. And why does it vary at any time scale? First of all, the main time scale that has been studied so far in terms of mean energy received by the solar radiation is the orbital time scale. The Earth goes around the Sun that basically control the seasons. When the Earth is closer to the Sun, you will have summer in northern hemisphere and winter in the southern hemisphere, because the Earth is also tilted around its axis of rotation. And when the Earth is farther to the Sun, you will have summer over southern hemisphere and winter over northern hemisphere. That's the actual situation. And you can see that the path of the Earth around the Sun is not a full cycle. It's like an ellipse. And its ellipse varies through time. It's more elliptical or more circular, depending on certain parameter of variability that we call eccentricity. And this circle is more or less elliptical, depending on this 400,000 year and 100,000 year cycle. That's why we call eccentricity. There are other parameters that will control the amount of energy received by the Earth, and this orbital parameter control the past climate variation that we all probably heard of, which we call glaciation and deglaciation. I don't know if you ever heard of this type of cycle. This is one of the main control of new climate change that occur on long time scale. When I mean long time scale, is like 100,000 years. So that explains why, for example, 20,000 years ago, we had a polar ice cap here over northern hemisphere that was very much developed. And this happened because the Earth was at a certain point quite far from the Sun for a long time. That allowed building ice cap, and that led to the Earth to cool and for a certain time. That's the last glacial maximum. So now, if we look also at other parameters, we have like the orbital parameter. We also have greenhouse gas concentration. We nowadays have a certain amount of greenhouse gases, but they also varied on long time scale on the past, and we know it because we had like natural archives that can tell us how much of greenhouse gases we had in the atmosphere a long time ago. Here I'm showing a map from the Antarctica and the location of various ice cores that were like analyzed in the past like 15 years. And in this ice core, when you look more in details, you can see that there is a lot of bubbles in this ice core. And in fact, if you look in these bubbles, you will find a paleoatmosphere, because the ice, the snow, when it fell, it was trapping part of the air at the same time. It got packed and it got trapped for until nowadays. And these are a good way to explore past variation of the composition of the atmosphere over quite a long time scale. And actually, the longest time scale that were recovered from this ice core are located in Antarctica, and they cover the last million year, basically. And here is a result that was published in 2006 that showed the evolution of the concentration of CO2 and methane. Don't look at this curve. That are the main important greenhouse gases that are at work in the atmosphere. And you see that there are large variations. Basically, during a warm climate period, an interglacial, we have about 280 ppm, which is a measure of concentration of CO2 in the atmosphere, as opposed to a glacial period where you have like a very low concentration of around 200 ppm. So on a glacial, interglacial time scale, you have large variation of CO2 that accompanied the climate change. If you put in perspective this natural variation that we had over the last millennium to what happened over the last century, here 0 is actually the beginning of the industrial period, and you can see that the concentration of CO2 increased like drastically over the last 100 years to reach 400 ppm, so quite a large level that were never reached before, at least over the last million years. So now that's a few elements to understand the new climate, what drives the new climate, and its variation on natural long time scale. But there are other processes that can also control climate variation, but on shorter timescale. What I mean shorter here, I mentioned timescales that are relevant for us. That means like a change from one year to another, or a decade to another, or a century to another. For example, the climate that our grandparents knew is quite different to the climate that we have today. So for those timescales, we can't involve or use as explanation the orbital variation of the Earth around the Sun, or the low frequency oscillation of the concentration of greenhouse gases on the atmosphere. Because these processes occur on a very long time scale, lower time scale. So for this shorter time scale, we need to find other explanation. Here, for example, I'm showing temperature variation on the last century. Global average for the whole planet, temperature anomaly. And we can see that there is an increase of temperature that reached almost 1 degree Celsius over a century. These variations are also occurring at internal time scale, and then we need to understand why. Here's an example for Mexico that is quite similar to what I showed for the global mean. This is the station that is the closest from the Mexico City, and we see that the early part of the century was much colder than the later part. We see variation from year to year. The bar are for a year average, while the black line is for a 5-year smoothing. So we have also about 1 degree Celsius of warming. So there is a long-term trend of increased temperature and variation that occur from year to year. So what is the origin of this long-term trend, and is it something that is significant? So to understand that, we need to go in more detail on other external forces that can work at those time scales. For example, we know that there are volcanic eruptions that occur once in a while, like for example El Chichón that occurred in Mexico like in the 80s. We know that solar variation can also vary on shorter time scale, and of course greenhouse gases that also evolved over the last century. So why volcanic eruption? I mean, we know, thanks to Pinatubo, that occurred in the Philippines in 1991, that this kind of eruption can have a quite large impact on climate. When I'm saying like thanks to Pinatubo, it's because it was the only eruption that was well observed, the only eruption that occurred during the satellite era. And we know that after this eruption, the climate cooled. This is anomaly of temperature on global average. This is the occurrence of Pinatubo eruption. This is 91, 92, and we see that we lost about half a degree in temperature. Half a degree doesn't seem like a lot, but in fact it is a lot. And that can explain, for example, the wiggle that we saw on the global average curve that I showed earlier. So how does that work? In fact, this eruption tend to emit a lot of ash in the atmosphere, but also gases. These ashes are washed out of the atmosphere quite rapidly by precipitation, because it stays in the lower atmosphere. As for the gases, like sulfate gases, they tend to be emitted very high in the atmosphere by this strong explosive eruption. And when they reach high level, these gases are converted through a chemical reaction in a particle of aerosol. And these aerosols are transported all over the globe by the atmospheric circulation. And quite rapidly, like in 5 months after the eruption, the whole planet is shed. There is some sort of a cover of aerosol that tend to reflect back to space solar radiation. This was well observed. For example, this is an anomaly of top of the atmosphere radiation change that occurred after Pinatubo. Here, this is the anomaly in watt per square meter. This is year 91 to year 95. The black curve here, it's not too visible here, correspond to the short wave radiation, so the energy received by the Earth in anomaly. And we can see that we lost about 6 watts per square meter a few months after the eruption. So that's a clear measure of the loss of energy that we receive from the sun due to the presence of aerosol in the atmosphere. And this is the evolution through time, and we can see that over the following years, this disappeared, and we went back to previous level that preceded normal level that preceded the eruption. So that we can see that the impact is short-lived. It's large, but it doesn't last more than 3 years. Now, what about sun spots and sun variability? Again, we learned a lot about sun activity after the beginning of the satellite era. And here is a picture of one of these satellites that shows a sunspot that occurs at the Earth's surface. And when we have a lot of sunspots at the sun's surface, the Earth tends to be more bright and it emits more solar radiation. So we receive more energy at the Earth's surface. And during other periods, the sun is more quiet. There is less sunspot. And during those periods, we receive less energy. And the cyclicity between the very active sunspot periods respectively to lower active sunspots occurs around an 11-year cycle. This is what was reconstructed here from satellite observation from 1975 to 2005. We see that they are like very regular cycle, and during the maximum we receive like more than 1 or 2 watts per square meter at the Earth's surface. As for solar variation over the past, there are also ways to reconstruct solar activity through natural analysis of natural archives. And here is the complementary picture of these cycles, but going back to the 1600 years. And we can see that during certain periods, there were very low sun activity. So we received, during this period, for example, much less solar energy. And even more or less here during the Maunder minimum, where there were absolutely no sunspot. And this is a period that we will discover a little bit later in terms of climatic impact. This is what we think caused the Little Ice Age. So now we explore the external forcing, but there are other processes that control the climate variability from year to year to decade. That's what we call internal variability. And one of the mechanisms that you probably all know that is a good example of internal variability, that means that occurs spontaneously because of unstable coupling between the atmosphere and the ocean. This is the El Nino oscillation. And during this El Nino situation, we have like warm anomaly over equatorial Pacific that I think you all heard about. And when you have this kind of anomaly, you will have like a large-scale impact. These warm anomalies are also like associated a few years after by cold anomaly. The warm anomaly are called El Nino, and the cold anomaly are called La Nina. So here this is a time series of the observed alternance between El Ninos and La Nina over like since 1985, I think, 65, towards the 2012. And during the warm El Nino event, we have like a large impact, climatic impact, because warm anomaly will disturb the atmospheric circulation over large scale. And over Mexico, more specifically, El Nino tend to bring more wet condition and colder condition. And you probably all heard about the ongoing El Nino. That is probably one of the biggest that was ever recorded. We don't know yet, but it looks like it. You can expect to have a very cold winter. I think you probably all felt that it's more cold than usual. That will have like many types of impacts. The warm water here associated to El Nino will tend to impact fisheries because fish species will tend to go away from the too warm water. So probably will have an impact on fisheries. And also you can expect to have more stormy weather. However, for the coming summer, expect to have like much more dry conditions. Usually El Nino warm events are associated to drying, so drier conditions. So this is an example of internal processes that occurs spontaneously and that doesn't involve any external factor that will alter the natural climate. So now we know all about that. We can go a bit further and summarize. If you look at a curve like this, you will see like various signals, you will see like a trend, and you will see like anomaly around this trend. So if you assume that the time scale that goes with this curve, here's an example for France, this is 1st of March, this is 30 of May, so you go towards summer. This curve, in fact, would simply relate to the Earth orbit around the Sun. This is season. So you get warmer because you go from spring to summer. So this is the orbital control of climate. Okay. Now, if you know that this is like a week-to-week variation, this anomaly around this orbital control warming are mostly due to internal variability, spontaneously occurring at big time scale, let's say. That's what we call weather. So the weather occurring at the daily time scale plus the slow variation of orbital variation around the Sun will give you the local climate here, for example, in spring occurring in Paris. Now, if you assume that this scale is not weekly but yearly, you can't involve the solar variation to explain this trend. You need something else. And also for the anomaly, you can't just involve like weather and stochastic modulation of variability. You can also involve like volcanic eruption, because I just show you that this type of eruption can disturb and cool the climate over several years. And also solar sunspot. But most importantly, for the long-term trend, this is probably due to something else that can be explained by solar variation, volcanic eruption, or solar activity. And this is due, in fact, to greenhouse gases concentration that is increasing through time. And the amplitude of the anomaly that are occurring at decadal timescale or internal timescale are much smaller, though, as compared to daily anomaly. So now we have all the elements to understand what control climate, what is climate, what control climate variability on very long time scale, like millennia time scale, what control climate variability from year to year. So on top of that, what human activity are doing. What are we exactly, how are we exactly disturbing these natural processes? So there are like several evidence that there is a global warming. I already show you this global warming picture that is a direct measure of the increasing temperature over the globe, plus 1 degree Celsius. Here, this is another way to see it. This is decadal average. So the decades we are in is the warmest decade over the century. And if you look at the signature, the global signature, the warming trend over the century is global. You see that the warming is occurring everywhere. So this is a first evidence that there is a global signal that the climate is getting warmer. There is other evidence. For example, the sea ice cover in spring in northern hemisphere is decreasing. There is a significant decreasing trend. This is snow cover, and here this is sea ice over the Arctic that is also decreasing. This is another way to see it. This is the ice cover in 2012, and here in 1982 there is a drastic reduction of the ice cover. So now we know that the climate is changing, that there is a global warming, and that is real. How do we know that is us that is causing it? That is due to human activity, because climate can vary naturally. To understand that, we need to put in perspective the recent climate change that have occurred during the last century. This is the upper panel here. Basically, this is the curve that you have already seen. We have also a long record, instrumental record. The longest record that we have are from England, and I think they started in 1900. So we see that there is a long-term warming that seems to have started way before the beginning of the industrial period. And to put in perspective this change, we can go back in time and reconstruct temperature change relying on natural archive. That's what we call paleoarchive.